Welcome back. In this video, we're going to talk about Lewis structures. Before we can dive into Lewis structures, we have to talk about covalent bonding. So let's remind ourselves that covalent bonds are generally made between two nonmetals. Because these nonmetals have similar electronegativity, what they do is they share their electrons in their bond. Whereas ionic bonds ended up transferring electrons in order to form ions. So these atoms are going to share their electrons so that they feel like they have a full outer shell. A lot of times that shell is called an octet because in organic chemistry, we're usually talking about carbon, nitrogen, oxygen, and fluorine, which all follow the octet rule. Whereas you learned in general chemistry, there were plenty of atoms that didn't follow the octet rule, and it felt more like a guideline. So when we draw our Lewis structures, what we're doing is we're drawing a representation of that molecule and which atoms are attached to which. In order to get to the point where we're drawing a Lewis structure, we need to be able to figure out how many valence electrons each atom has. Because when we make the Lewis structure, what's going to happen is we are only allowed to draw the valence electrons for that entire molecule, because the core electrons aren't involved in bonding. So at this periodic table at the bottom of the screen, let's look at how many valence electrons each element has. So I've highlighted here some elements in yellow because these are our main group elements. These are the ones that have the most utility, both in general chemistry and in organic chemistry. You save those transition metals for later. Now, the numbers across the top here, so this number 1 is saying that this column has 1 valence electron. That matters for us in organic chemistry because hydrogen is in that column, so we need to know that hydrogen has 1 valence electron. Then everything in this column has 2 valence electrons. We will skip the transition metals. Then we get to column 3, which has 3 valence electrons. Finally, column 4, where carbon is, has 4 valence electrons. And then we keep going until we get to column 8. Now, in column 8, helium, which is right here, doesn't actually have 8 valence electrons. It only has 2. So in some periodic tables when you're counting valence electrons, they'll end up drawing helium over here. But as long as you remember helium only has 2, that's fine. And honestly, you won't really have to know that for organic chemistry at all. That's more of a general chemistry idea. Because in organic chemistry, we're basically going to be using hydrogen, carbon, nitrogen, oxygen, fluorine, and sometimes some sulfur and phosphorus, and the rest of the halogens. So this is what matters to us. We need to be able to count the valence electrons. Let's talk about why covalent bonds are going to form. So I have the beginning of a graph over here on the bottom right-hand side, and I have potential energy versus internuclear distance. And I have my hydrogens here drawn really close together, right? This is too close. So remember that your hydrogens have a nucleus where the protons are and an electron cloud around it. And so what's happening is that in order to form a bond, your hydrogens, and I'm just using hydrogen as an example here, are going to get close enough to one another that they can share those electrons. But if they get too close, then there's repulsive forces that occur, and the potential energy is high. Whereas down here, my hydrogens are at a perfect distance. They're at a minimum of potential energy. They've balanced their attractive and their repulsive forces. And then over on the very right, I have 2 hydrogens that are just not interacting with each other at all. They're 2 singular electrons, which are called radicals, and they're not in a bond. So if we put a graph to this, this is our highest energy. Over here is our lowest, and then we level out over on the right-hand side. So our bonds form because what is happening is when 2 atoms come together, they find a position where they can share their electrons and create a stabilizing effect and be close enough that the repulsive forces aren't too repulsive. And so it's almost like the Goldilocks of distance, right? Here is too close, too far away, and just right. So why do these bonds form? It's always about stability. There's a stability, a lowering of potential energy. Than they would be if they were separate. So there's lower potential energy in a bond than if the atoms were separate. So now that we know valence electrons, we know why the bonds form, let's talk about actually drawing Lewis structures. So let's talk about drawing Lewis structures. I want to lead us through an example, and let's do nitrate. So for nitrate, what we want to do first is we want to figure out how many total valence electrons there are. So we use our periodic table to remember that nitrogen has 5 valence electrons. And I'm going to abbreviate valence electrons with VE, V for valence, E with a negative sign for electrons. Your oxygen has 6 valence electrons, and in your structure, you have 3 oxygens. So you have a total of 18 valence electrons just from the oxygens. So what about that charge? Well, if you have a negative charge, you add that many electrons. If you have a positive charge, you get rid of that many electrons. If there's no charge, you don't do anything. So we have 1 additional electron from the charge. So we put all of this together and we end up with 24 total valence electrons. Mind you, if you end up with an odd number, usually something is amiss because very early in the semester you have not learned about odd number of electrons yet. So double check your math if you end up with an odd number. So I'm going to draw the skeleton where nitrogen is my central atom. So I'm going to put that one in the middle. And then I'm going to add my oxygens. Now I can count how many electrons I've drawn. So each bond is worth 2, so I have drawn 2, 4, 6 electrons. So if I just try to keep like a tally off to the side, right, I had 24 valence electrons and I used 6. So I have 18 valence electrons left. Now what I want to do is I want to fill the octets for the structure. I like to start with my outer electrons and begin putting my octets on the oxygens. So I just used 6, there's 12, there's 18. Remember that if you have hydrogen present, hydrogen can only take 2 valence electrons, so it's done after 1 bond. If you end up using beryllium or boron, remember they also do not follow the octet rule. Thankfully, most of the time, the only atom that you're going to encounter that doesn't follow the octet rule is hydrogen. Then we're going to fill the octet on the central atom. Now, we've used up all 18 electrons, so we're done. We have 0 electrons left in our bank. So in our particular case here, we can't add more electrons to the central atom because there aren't any more to add. So what we need to do is have the oxygens share more. So I want to focus really quick on the nitrogen. I'm going to erase my blue highlights and come in with some yellow here. Focus on that nitrogen and recognize that we have 2, 4, 6 electrons around that nitrogen. That's not an octet. Nitrogen does follow the octet rule. So what we're going to do to satisfy nitrogen and give it its octet is one of the oxygens is going to choose to share its pair of electrons with nitrogen. So we're going to take 1 pair off of 1 oxygen. It doesn't matter which oxygen, it doesn't matter which pair, and we're going to put it between the nitrogen and the oxygen. So I'm just going to redraw my structure. So now I'm going to have a double bond between nitrogen and one of my oxygens. This one only has 2 pairs on it now, and these still have 3. So I have successfully created the nitrate ions Lewis structure. If we would have had more electrons, then we could have just put the extra electrons on the nitrogen, but because we had 0 electrons, we couldn't do that. Let's do some more examples. For this, I would actually like you to pause the video and give these a try before you come back and hear my explanation for them. So I'm going to give you an opportunity to pause, give them a try on your own, and then come back and we'll compare some answers. So let's come back and look at this together. So I have already gone through and figured out how many valence electrons each of these structures have. Now let's go ahead and start building the structure. So if we start with CO2 on the left, carbon is going to be your central atom here, right? Your inorganic chemistry, a lot of times carbon is going to be your central atom. When you are unsure, you can use guidelines like the least electronegative atom is often the central atom. If you only have one of a single atom, that's often the central atom. Hydrogen cannot be the central atom. Things like that will help you figure out what the central atom is. So now let's attach our oxygens to each side of the carbon. Now, I drew them in a linear fashion because I know about molecular geometry. You might have drawn yours bent. That's fine for right now, and we'll expand upon it later. So I've drawn in 4 electrons already because this is worth 2 and this is worth 2. So now what I have left is 12 valence electrons. So let's go in and start putting in those valence electrons. I'm going to put them on my exterior atoms first. So I've filled up the octet for the left oxygen. Now I'm filling up the octet for the right oxygen. Now that I've used up all of my valence electrons, because I just used 12 of them and now I'm at 0, I need to look at this and decide, do I have an octet on my central atom? And the answer is no. Carbon only has 2 bonds around it right now, which is 4 electrons. So what needs to happen? Sharing. So let's take a pair from one of the oxygens and we're going to remove it. So I removed 1 pair. And now I'm going to draw in another bond there. So I still have the same total valence electrons. I haven't actually added any electrons. All I did was change where the electrons were. Now I look at my carbon and I have 2, 4, 6 valence electrons around it. Not enough. I need another bond. So at this point, we end up deciding we need another pair of oxygen's electrons to form a bond. The question becomes, do I choose an electron from this side, we'll call it side A, or do I choose an electron from side B? And for right now, let's just recognize that nature loves symmetry, so we're going to choose from side B. And then when you get to learn about formal charge, you can really see why we end up choosing an electron from the right-handed side. So I'm going to just remove an electron from the right-hand side. I'm going to draw it as a double bond instead. Now I still have 16 electrons drawn, and my carbon, I will just erase my highlighting so I can recount, has 2, 4, 6, 8 electrons around it, and guess what? So do each of our oxygens. Now let's do the same thing with CH2O. Carbon is still going to be our central atom here. So I've got a carbon, a hydrogen, and an oxygen. So I've used 6 electrons. 2, 4, 6. So I have 6 electrons left to use. I'm going to fill my outer shell first. So I fill my exterior atom's valence shell. And I look at my hydrogens. They can't take any more electrons. So I leave them be and I put electrons on my oxygen. So now I check my central atom and carbon does not have an octet. And so what do? Share. So we'll take away one of the pairs on the oxygen and we will put it between the carbon and the oxygen. Now, hydrogens have their 2 electrons that they need. I like to call that a duet sometimes. Oxygen has its 8 electrons, carbon has its 8 electrons, and we've drawn a total of 12 electrons. At this point, I usually get some typical questions that I'd like to preemptively answer. One is students will look at how I drew this structure and notice that I drew everything 120 degrees apart or ish, and they'll say, do I have to do that? And the answer is not yet, right? We're going to get to the point where we review molecular geometry and electron pair geometry, and at that point, we'll get to be doing those things. The other thing that people will ask me is, when you're looking at the oxygen, does it matter where I put the pairs of electrons? And that's actually kind of like the same idea, right? If you ended up putting your electrons, one on the left and one on the right, one on the top, one on the left, it doesn't matter in the grand scheme of things. In real life, those electrons will repel each other to get as far apart as possible, but we're just drawing this on paper. So as long as your oxygen has 2 lone pairs on it, you are good. Now I want to move into structural theory a little bit, because the amount of work that we just put into drawing very simple Lewis structures was ridiculous. And in organic chemistry, we don't have time for that. So what we need to do instead is start to recognize that there are some patterns. Carbon is something that's called tetravalent. That means carbon tends to form 4 bonds. Nitrogen is trivalent. That means it tends to form 3 bonds, and it also has 1 lone pair. Oxygen is divalent, which means it forms 2 bonds, and to make its octet has 2 lone pairs. Hydrogens and halogens are monovalent. They will form 1 bond. Hydrogen will have 0 lone pairs and 1 bond, whereas halogens will have 1 bond and 3 lone pairs. So one of the very special things about carbon is how it can use its valence electrons to bond to itself in multiple ways. Because carbon is tetravalent, it can bond to itself with 4 single bonds. It could bond to another carbon atom where one side of the molecule has a triple bond and the other side has a single bond. There's all kinds of possibilities as long as you end up with 4 bonds around carbon. Now, in the structural theory, hopefully what we're going to get to is that we're just so used to seeing certain patterns of bonding that we don't need to go through the whole process that we did in general chemistry, which we just reviewed on how to draw Lewis structures. One of the things that's imperative in organic chemistry is formal charge. For formal charge, you're looking at how many electrons an atom would prefer to have around it, which is its number of valence electrons. And you're comparing that to how many valence electrons the atom has around it in a particular structure. There's a whole bunch of ways to calculate formal charge. I'm just going to put in one calculation here for you that I find students like the best. So your formal charge can be calculated by taking the number of valence electrons for an atom, subtracting the number of bonds and the number of lone electrons. So not lone pairs, but individual electrons on that atom. Our goal for formal charge is to have the lowest formal charge possible and to have the fewest atoms experience a non-zero charge. When people write formal charges, a lot of times you're going to see folks write a charge with a circle around it, or maybe they'll put, like brackets, or maybe some people will just leave off the circle and the brackets completely and just write the positive and negative. Personally, I think that writing at least small brackets around it helps bring your eye to it so it doesn't look like a mistake, it looks purposeful. When you're looking at molecules or ions, the sum of your formal charges always equals the charge on the overall structure. So for example, on the left, I have the sulfate ion, and you know from general chemistry that the sulfate ion has a 2- charge. And so when we're looking at the sulfate ion, that means that we need to have a total of 2 negatives across the sulfate ion, and we do. The 2 oxygens that I drew negatives next to, each one is negative. All the rest of the atoms are 0. Something like carbon monoxide is overall 0, yet has formal charges. So this carbon is negative and this oxygen is positive. Net, so overall, there is 0 charge on carbon monoxide, but you can't get any better than that. That's the lowest formal charges that are possible for that structure. In organic chemistry, you don't have time to look up the valence electrons, write down a calculation, remember the equation. There's not time for that. So what we need to do is find patterns. Before I have you find patterns, I want you to go ahead and fill in the non-zero formal charges on these structures. And I'm going to pause, I'm going to wait for you. And then what I'm going to do is I'm going to come in and I'm going to do it. I'm going to show you how fast it can be done when you've seen the patterns. So I'm pausing, I'm waiting. Okay, hopefully you hit pause because it's hard for me to wait. Are you ready? Negative, positive, positive, negative. Okay, done. I didn't have to do any calculations and I did it rather fast. And now I know you're thinking, yeah, but you're the teacher. Okay, but once you get the patterns down, my students can do it that fast as well. So let's talk about how you're going to find the patterns. What I want you to do is I want you to fill in a table that looks like this. I want you to remember that carbon normally is tetravalent, which means it forms 4 bonds and no lone pairs. Nitrogen, we said, forms 3 bonds and 1 lone pair. Oxygen forms 2 bonds and 2 lone pairs. Halogens forms 1 bond and 3 lone pairs. So when these atoms follow their typical valencies, they have 0 formal charge. So what does it take to make carbon positive? What does it take to make carbon negative? So I want you to spend some time filling in that table and finding the patterns. You might need to draw some stuff out. You might need to fiddle with the formal charge calculation. Am I going to fill in this table for you? No. You know why? The person doing the work is doing the learning. Let's wrap up. In this video, we talked about what is a covalent bond. We looked at valence electrons, figuring out how they relate to the periodic table, and then being able to calculate how many valence electrons are in an atom or a molecule. We covered the Gen Chem rules for drawing Lewis structures, which was way too time consuming. So right now you're going to be able to draw small Lewis structures, but with practice and time, you're going to be able to draw bigger Lewis structures without using any of the rules that we went through today, because it takes way too much time. For formal charge, we also covered our Gen Chem version of formal charge, and then we ramped it up to organic chemistry, where instead of calculating that all the time, we're just going to figure out patterns. So once you're ready, fill in that table, and you will have formal charge down pat after a little bit of practice. And trust me when I say that there is not enough time for you to pause and calculate formal charge for every atom that you need to. It needs to become second nature. Thanks so much for your attention. I'll see you in the next one. This is Katoni signing out.